All right, folks. Sorry about that. Seems like there was a hiccup in YouTube over the last 10 minutes. So I think we're golden. Okay. So this is lecture 9 of ECE 3311, Principles of Communication Systems. Okay. And today we're going to be talking about the all-important topic of Nyquist filters. All right. So what did we see from the lecture 8? So just to recap, what we looked in lecture 8 is this concept of, and it's a pretty serious concept, of intersymbol interference, right? Where if we have an environment, the propagation medium, the channel that the transmitter and receiver are connecting through, there is a possibility that if that channel introduces some sort of distortion, that it could potentially warp, right, your transmitted waveforms from the so the transmitter is sending out, let's say, polar non-return to zero, for instance, as a good example, and it's all these rectangular pulses, and then the environment comes along and it distorts it, it stretches it out, it creates echoes of that, such that at the receiving end, what ends up happening is you don't get what was transmitted. You get some sort of messed up looking version of it. And potentially the distortion could be so severe that it could make the decoding of those transmitted signals after it's passed through that channel very difficult, potentially to the point of introducing or increasing in a non-zero fashion errors in decoding what has been transmitted. So we kind of looked at it a little bit. So let's actually switch to the following. Let's go to the whiteboard. Okay. So what we looked at before, all right, is lecture 8. Is something along these lines. So if we transmitted in the time domain, something that looks like this, right? That's my, as an example, polar non-return to zero. But without loss of generality, the impacts could be potentially the same. And suppose that's binary 1, binary 0, binary 1, binary 1, binary 0, right? And these are the 0, TS, 2TS, 3TS, 4TS, 5TS. What would happen is if there was some sort of distortion, and what we do is, let's say we drive that through something, HCFT, it's impulse response that characterizes what the channel, how the channel distorts that signal. So we have SFT, that's incoming, RFT, that's outgoing, right? What ends up happening is, first of all, that's at the transmitter. At the receiver, so first of all, if we have some sort of characteristic of HCFT, the impulse response looks like something like that. That's a problem. Because what would happen is, what ends up, how does the output look like given this HCFT? RFT is going to be equal to the convolution of HCFT with SFT. So what we end up getting is something that would look like this. We get this smearing impact, smearing distortion looking thing. So let me first. Okay. So what ends up happening is we have some sort of smearing across beyond just this, the symbol periods. Okay, so we get something like this. And because this impulse response is non-zero, right? The ideal would be a delta, right? So it comes in, it goes out. right? But convolution, what happens is it stretches, it distorts, it will manipulate the incoming signal, okay? And we have some sort of spread by some amount tau. What we get is something that will look like this. Something like that. And now it's like, does this look like a 1? Does that look like a 0? Or 1's here? We don't know. The receiver is now stuck with trying to make that determination. So this is the time domain, right, of ISI. From the frequency perspective, if we use rectangular pulses, right, described like this, for minus TS over 2 to TS over 2, the frequency equivalent is going to be a sync pulse, right? It's going to be TS sync pi TS F. It's going to look like this, right, to F. And you're going to have 0 crossings at 1 over TS, 2 over TS, minus 1 over TS, minus 2 over TS, okay? The problem with this waveform also, big problem, goes off to minus infinity and infinity. This is very impractical. Why? Since we don't have infinite bandwidth. Okay. BW usually, to me, is my shorthand for bandwidth. Okay. So we have these issues. So this lecture, what we're going to be coming up with, okay, lecture 9, right? So what Nyquist pulse shapes do is it tries to achieve 0 ISI, right? So that, like, if you use Nyquist pulse shapes, you're going to be golden in terms of avoiding any sort of like intersymbol interference. But okay, but heads up, this will only work. This will only work for pulse shapes that shucks. Like if you don't have any sort of channel environment in between, right? So this is under ideal circumstances. These are pulse shapes that you can use like from end to end, if you have an ideal channel. If you have a non-ideal channel, recall, okay, so no ISI. So this assumes that, again, an ideal HC. So recall that we had this yesterday as well, right? So we have that. We have a transmit filter. We have the channel filter. We have the receive filter, right? So, and so what happens is this guy is whatever our waveform is for, like, let's say, shucks, like a polar non-return to 0 or unipolar or Manchester and the like. And this is our channel environment, right? And so we only have control over that and over that, right? That's my TX and RX filters. Cool beans, right? So those are the things that we can control. So the Nyquist filters, what they do is that that allows us to create these waveforms that like eliminate any sort of ISI. So essentially, when we transmit them, we don't have any of that energy spill over into the next symbol, gets sampled as well, and distort the value that makes the receiver question whether it is a 1 or a 0. So it makes so hopefully these 0 ISI pulse shapes will actually help us at the end of the day. So what are some of those pulse shapes? So first of all, what's the condition? So obviously, just as another aside, I hope I'm not going to be doing too many asides today. Okay, so first of all, that's also from lecture 8. Okay. So on the side, we also know about like Nyquist rate, right? That should have been from discrete time, signals and systems, right? And that, okay, is a separate rule or sort of entity, right? That's when we were trying to sample, let's say, an analog signal in order to into a digital form, and then it's the rate at which we can reconstruct that that analog signal from these discrete samples without any aliasing, right? So that's a separate entity. Nyquist Paul shapes is different. Okay, so let's go back to the slides. Here we go. Okay, so here, what we want to do is we want a target equivalent transfer function, okay, such that, so this here is kind of like that rule like, that we need to do, which is the equivalent transfer function is equal to the following: that if we were to take that that transfer function, that waveform, and then take a copy of it, and then shift it, okay, shift it by an integer multiple of the symbol period, okay, and then suppose there is some sort of timing offset between transmitter clock and receiver clock. That's also very that happens a lot. So if you take my software-defined radio class, I'll be talking a lot about that, like, you know, in terms of the timing offset between two radios, right? Because they both have their own crystal oscillators, therefore their own clocks, and therefore you have to account for that time difference between the two. So the tau is really important, just for the sake of aligning the transmitter and the receiver in terms of the symbols that come across, so you sample at the right point at the receiver what has been transmitted. So what does this mean? So this is what this means. Let's go back to the whiteboard. So what does this mean? So at HE integer, right? So K is an integer index. I always spell integer sometimes incorrectly. Integer index, right? TS, that's my symbol period. Okay. So this thing, this waveform, right? And what it will be is it's either equal to a constant C, or otherwise 0. And what we need to be mindful of, okay, is that the following. Oh, shucks. Okay, so what happens is that we have to have this waveform such that when we have these multiples, right? So when what this translates into is if you have your equivalent waveform, right, and you take a copy of it, and you take a copy of it, and you take a copy of it, what should happen at the end of the day is that it should be at a constant level, right? At each one of these instances. And then, of course, you have the tau that accounts for any sort of delay between the transmit and receive clocks, right? So what ends up happening, so how does that work again? Well, let's look at this. Shucks. Sorry, I didn't even. So let's go back to the expression, this thing here. All right, so what does this mean? Okay, so what ends up happening is this fella here, the way this would look like is the following. Let's leave that out. So suppose you have 0, you have TS, you have 2TS, you have 3TS. Okay, and then you have minus TS. And you have minus 2TS, minus 3TS. And they go from minus infinity to infinity. So what this means, so let's assume alignment between TX and RX clocks, okay, CLKS, right, clocks, already performed. Okay, so therefore, I'm going to let tau equal 0, just for sake of simplicity, right? So they're perfectly aligned. What this means, this rule here, is that I have this. So my equivalent waveform needs to satisfy this. What I mentioned before with the copies and stuff, my mistake. What happens is that's what happens in the frequency domain. Okay, and that's so there is a time domain representation. This is it, right? So what this means is my waveform, my HE of T has to satisfy this to be Nyquist, right? In the frequency domain, what it turns out is that if you take the Fourier transform of this requirement, okay, and we're not going to go into the derivation in this lecture. It is described in the textbook. What happens is this is equivalent to taking the frequency representation of HE of T, which is going to be HE of F. And what happens is if you space that out, okay, periodically, the sum of that frequency response should be a constant as well, right? But that's the frequency version of the exact same rule that we have here for the time domain. And so, like, that's nice, but I can't transmit deltas. Well, you don't. You can create any sort of waveform that you want. You know, it could look like this, but as long as it's one over here, and has 0 crossings everywhere else. Okay, this of course is extremely exaggerated, but the reason is we have to have this waveform is for the following. If I were to employ ultimately, so my HE of T, recall, okay, we have that. So ultimately, okay, what we want is a Nyquist pulse shape. Where if we transmit symbols at 0, TS, 2TS, 3TS, 4TS, 5TS, 6TS, okay? What should happen is that we might have a melange. So let's take that example again of 1, 0, 1, 1, 0. I'm going to add a 1 here, right? And 0. So what should happen, and let's say that's represented, so a 1 is represented by a plus a value and a 0 is represented by a minus a value. So we should have, at that sampling instant, plus a, minus a, plus a, plus a, minus a, plus a, minus a, right? And then some sort, let me, again, I'm not really a great artist. Something like that. All my receiver cares about is that sampling instant, that sampling instant, that sampling instant, that sampling instant, all of these. And frankly speaking, all the stuff in between doesn't amount to a pile of beans, because what will happen is When my receive radio, it's going to first of all digitize the incoming analog signal. So it's going to sample very specific instances. That's why tau is actually kind of important. In order for the two to be on the same page, for them to be synchronized in time. What ends up happening is, once you know exactly where the sampling instances are, what this means, going back to the Nyquist pulse shapes, going back to this very important rule, all right? What this means is that, so what if the waveforms overlap with each other, like what we had before, because of the environment? What ends up happening is if I design a transmit and a receive filter, I have a channel filter, and I have my original pulse shape that results, let's say, from line coding. As long as the sampling instances ultimately that determine whether it's a 1 or a -1, a 1 or a 0, as long as those are not interfered with, doesn't matter what's in between them. And that's what the Nyquist pulse shape does. So what happens is, this is ultimately, if I can design my HT of t and my HR of t such that even with, okay, so I mentioned initially, this should be ideal. Now, I take it back. What happens is, if I have a really bad, very dispersive, really distorting type of HC of t, but I design HT of t and HR of t with H of t, an H of t I don't touch, but such an end-to-end as Nyquist doesn't matter. So that's what I'm ultimately striving for. Okay, so let's go back to the slides. Because remember, your receiver, all it's going to care about is that one sample. Is it plus A or is it minus A? And then it's going to map it to 1 or 0. Okay. So one waveform that achieves that, we've seen this before, is the sync pulse. It absolutely 100% achieves that, right? So yeah, I'm just flipping back and forth, right? So sync pulse, absolutely awesome waveform. What it does is the following. I drew this before. So a sync pulse looks like this, right? So sync, right? We don't have to put the T in front of it. Okay, let's scrap the T. Boop. So pi TS F, right? What this is going to look like is exactly what we're looking for. Let's say it's 0, right? It's 1. Goes through the first 0 crossing, second 0 crossing, doop, 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 from -infinity to infinity, right? So here it's 1. Perfect. Totally Nyquist. 0, 0, 0, 0, 0, 0. So suppose I now have a cascade of these things, right? 0, TS, 2 TS, 3 TS, 4 TS, 5 TS, 6 TS. And suppose now I want to take this as my resulting HE of t. So what should this look like? So let's say I pass every waveform through. And what's interesting here, folks, is the fact of how we construct this, right? So I could send an individual pulse, right? So remember how we modeled this at the beginning. So if I had something, remember this? And this could be either plus or minus A, right? And that represents either a 1 or a 0, right? Delta T plus NTS, correct? So what ends up happening is, first thing it does, convolve it with H of t. So now we have the polar non-return to 0 train, right? And then it passes through the H of t and the R of t and the HC of t, right? So HR of t, HT of t, HR and HC of t. And if we design of t of t, ht of t and hr of t, such that we get an equivalent response that looks like that. The way we can treat this is, since this is just a train of these deltas, we can sort of divide and conquer. So these are all time-shifted deltas with either a plus a or minus a amplitude. So what we could treat, again, because convolution's a linear operator, so summation and everything like that. So remember that the output, right, after the H equivalent, so this could also be convolved with HT of t, convolved with HC of t, convolved with HR of t, such that all of this, remember, has representation HE of t. What we end up getting is something that looks like this. So brace yourselves. This is going to require a lot of art skills. So I'm going to have the first. So let's say the first fella is a +1. So that's going to be plus a. So by linearity, I'm going to do the following. So that's the first sync pulse. That's this thing. Let's say the second thing is minus a. Different color. Let's use green. That's minus a. There's a zero crossing. Oh, that's so important. So just quick FYI, look at this. At 0, it has a non-zero value of a. And every other sync pulse I'm going to draw is going to go through the zero crossing. So theoretically, only a is going to be registered, not a plus other stuff from other symbols. No ISI. So it's beautiful. Let's go back to this thing. So, and then, again, not an artist. But then let's take the next one. Let's say the next one is a. So plus a again. So that's going to look like passes through that zero crossing, passes through that zero crossing, and then here passes through that zero crossing, that zero crossing, that zero crossing, that zero crossing, right? So the zero crossings are critical, except for the desired sample, which will be non-zero at the correct sampling instant. Everything else is going to be like everything else is going to be zero. So that's zero ISI. So let's look at it. Let's look at this. So here, non-zero, non-zero, and this is the target. This is the target value. Here, we have two other contributions, okay, from the previous two samples. They're zero, right? So if you look at the end of the day, if what you'll have is you'll have plus a, which is what it should be. No other contributions, no intersymbol interference, right? So that's Nyquist in action. Now, let's go back to the slides. Okay. So there is, unfortunately, kind of a problem. Actually, let's switch gears one more time. One more thing. So I mentioned about the frequency equivalent, right? The frequency equivalent of HE of F, and how if you sum up HE of F, right? So what it should look like. So let's say we look at the Nyquist pulse shapes, like what makes them Nyquist in the frequency domain. So what is, like, let's look at an example. Let's look at a sync pulse. What is it in the frequency domain? Boop, 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 boop. It's going to look like that, right? There's a duality. So the Fourier transform of a sync pulse, right? What is it going to be? It's going to be a rectangular frequency response, right? So what's going to happen is, oh, sorry, let's just, so what's going to look like is the Fourier transform of a sync, it's going to be rectangular. It's going to be this frequency response, right? And what Nyquist pulse shapes have to do equivalently is if we take it and shift it, right? Okay, by 1 over Ts and minus 1 over Ts, and then minus 2 over Ts and 2 over Ts, and all to infinity, what we should have is a constant, C. So that's the equivalent. So if you work in the frequency domain, that's what you should be getting alternatively. Okay, so time domain, all the samples, every Ts seconds should be 0 except at the desired instant. The frequency domain should be a constant if you take the frequency representation of the Nyquist pulse shape, and then you take it and its periodic replica at 1 over Ts, bloop, 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 you'll get that. Okay. There's a problem, though, with sync. What's that problem? The problem is sync, just like in the frequency domain, sync is defined from minus infinity to infinity. So you say, oh, well, so what? Well, here's so what. Trying to find a waveform that will go on your radio that is specified from minus infinity to infinity. You don't have infinite memory. So this is actually kind of a really serious problem. So the thing is, you either can build radios or circuits or whatever that can have infinite memory, or the alternative, you truncate sync. So instead of like, from minus infinity to infinity, suppose you do this. And you might say, oh yeah, that's genius, right? No, because this, okay, is not, if you take the Fourier transform, it's not equal to that. It doesn't satisfy Nyquist, right? So what will end up happening is, what you will get is something that will look like this. So it's going to be, you'll get these imperfections. We call it a Gibbs phenomenon here. So it's not a perfect rectangular pulse, and therefore, if you sum copies of this, you're not going to get a perfect constant, and therefore it doesn't satisfy the frequency constraint of the Nyquist criterion for 0 ISI, right? So that's Gibbs phenomenon. And then here as well, if you truncate the sync, you're not going to get this perfectly occurring at integer multiples of Ts. You just won't get 0 crossings. So 0 crossings at multiples of Ts? Nope. So already this type of waveform is going to be violating the 0 ISI condition for these the Nyquist conditions for 0 ISI. So that's not so good. All right. So okay, so this doesn't work. So HE of F got to be perfectly flat. Not going to happen if you truncate a sync pulse. And then the problem about in the time domain is that you can't have it go from minus infinity to infinity. If you truncate it, you don't have a sync pulse anymore. And it doesn't satisfy the time domain requirement or the frequency domain requirement. So very impractical. So alternatively, there's this thing called raised cosine pulses. From this point onwards, if you haven't heard about it and you're going to go into the communications world, raised cosine pulses are everywhere. Like, I mean, everywhere. So you're going to see it in every communication system, right? So, so what the raised cosine pulse looks like, okay, the way it's defined here in the frequency domain, okay, looks like this. So what you're going to have is your H equivalent, okay, of F is going to be something that it's going to have a flat portion up to F1. There's going to be this transition area, transition band, and that's going to have the shape of a cosine, half a cosine. And then outside of the transition, 0, right? So it's going to look like this. So raised cosine, pulse shape. So this is sometimes abbreviated as R-cos. Okay. So the way this would look like in the frequency domain is something like this. It's a 0. There's a plateau. And that goes from Nyquist, from 1. There we go. From minus F1 to F1. And then here's your half cosine function, right? This is literally half a cycle of a cosine function. And it goes to from minus B to B, right? So what's interesting about all of this is that you, as the engineer, can actually design, how stretched out or how compressed. Like, so this is your transition bandwidth here too. You can design that, right? So that's flat, that's 1. And then you can, and this is your overall bandwidth, okay, of the frequency response. So let's say this is your HE of F. And then you have your transition bands. And what you can do with a raised cosine pulse, okay, is the following. So this is the representation. Also notice, like, it's literally a cosine function. It's, instead of going from -1 to 1, like a regular cosine, so it's lifted. So it has a bias, so it doesn't go below 0, right? And it's also shifted in time, so to complete that half cycle. And so what B is what we call the absolute bandwidth. Like, this is the entire pulse shape in the frequency domain, right? Because people also look at things like, for instance, the 6 dB bandwidth, right? And you say, huh, what, 6 dB bandwidth? So that's when, so think about it. 6 dB bandwidth is when the energy, sorry, the amplitude, the magnitude of the frequency response goes down by 50%. So that would be here. So this is important. There and there. F0 minus F0. Okay. So what's interesting, okay, is if you change the specs of this, everything pivots on this 6 dB point, right? It's 50% down from the plateau, okay, from the passband region. So if you do that, so you have the 6 dB bandwidth, you have the absolute bandwidth, then you also have this thing, right, which is the delta, the F delta. So where does that look like? Here. F delta is this thing here, or delta F, right? Same thing here. Delta F or F delta, whatever the nomenclature you want to use. And then over here, okay, you also have like what F1 is, right? F1, the value. And that fellow there is in the opposite direction. You can define that. So, but this is the important thing. Whenever anybody speaks of raised cosine pulses, they talk about Rolloff factors. And this is a value that goes between 0 and 1, right? So this is actually really important. So what this says is the amount that your raised cosine pulse rolls. And like, what the heck does it mean to roll? This is what I mean. So what I could do with a raised cosine pulse, these are all, I'm going to draw the frequency responses raise cosines in frequency. So these are all valid raised cosines. So I can have, let me draw this better. I could have the following. I could have like what I just drew, right? That's valid. I could also have this. I could, so there's a smaller, so that's quite large, that one, like, you know, so let's say that's minus F1 to F1. That's a much narrower one. I could also have a much more aggressive, let's see, that. Right? Minus F1 to F1. So all of these are raised cosine pulses, but they each have a different Rolloff factor. R, right? And this really depends on how you want to, like for whatever application that you're using these raised cosine functions. And because one thing you want to be mindful of is the fact that, you know, when you're transmitting information, you know, these raised cosine, their absolute bandwidth, potentially if you have adjacent communications, how do you want these to go over, spill over or not, right? So if we go over again to the expression here, this is the frequency domain representation. And this, like what I just described, there's a lot of frequency domain content. This is its equivalent time domain representation, right? So if ultimately, if you're targeting your equivalent end-to-end HT, HT of T, HC of T, HR of T to look like in the time domain, this is what you'll be shooting for. And it's less intuitive what the heck this looks like. But because this satisfies the Nyquist criterion for zero ISI in the time domain, chances are if you plot this out, it's going to have zero crossings at every other sampling instant, an integer multiple of TS, and at the desired sampling instant, it's going to be 1. Okay, so check it out. All right. So, what are the lessons learned from this lecture? So lessons learned from this lecture are that we have, so let me summarize. What we have is the following. In lecture 9, we saw Nyquist criterion for zero ISI, right? So we saw what had to happen in the time domain and the frequency domain, right? So in the time domain, we at integer multiples of TS at the desired instant it has to be 0, and every other instant it's got to be non-zero, and every other instant's got to be 0. Frequency domain, the periodic replicas of HE of T, or the frequency response of that, need to sum up as you go from minus infinity to infinity. It's got to be a constant. Then we saw how sync pulses achieve that but are impractical, and how raised cosine pulses are great, but the problem there is that, well, actually there isn't any problem. This is actually, so this has problems. So I'm going to put this, on the other hand, is used a heck of a lot in a lot of applications. You're going to see this used a lot, even in this course, okay, and any follow-on communication courses. So unfortunately, because of the technical difficulties earlier in this lecture, trying to get things going, I don't have any time to actually go through a solved problem, but I will do that at the beginning of the next lecture, for lecture 10. So with that, this concludes lecture 9 of ECE 3311, Principles of Communication Systems. All right.